Welcome. This is 6.3 Exponential Functions. Guess what we're doing more of today? Graphing. My goodness, I know, exciting. Okay. We're graphing a new function, though, an exponential function. Okay, so the definition of an exponential function is a function of the form f of x equals c times a to the x, where a, the base, is a positive real number, and the base has to be greater than 0 and not equal to 1. And c not equal to 0, that is just a real number. It could be a constant or coefficient. The domain of an exponential function is a set of all real numbers. The base a is the growth factor, and because f of 0 gives us c, c is called the initial value. So this will come in handy, like with that whole c a of x, when we start getting into what is it? I think it's 6.8, uninhibited growth and decay. So once we get into those models. Today, just graph exponential functions, learn what they are, and solve exponential functions. Okay. Examples of exponential functions: 2 to the x, 1/3 to the x plus 5, and 2 times 3 to the x minus 3. These are all examples of exponential functions. Okay. Also, when you guys are graphing them, you should also notice that you can apply transformations. So this plus 5 would be a vertical shift up 5 units, just like we know. This 2 in front would be a vertical stretch by 2 units. This x minus 3 would be a horizontal shift to the right 3 units. So you see how you can apply transformations to exponential functions. You can apply transformations to any graph of any function. Okay. Notice for each function that the base of the exponential expression is a constant and the exponent contains a variable. So for exponential functions, we see that x is always the exponent. Okay. Now let's go ahead and graph the exponential function 2 to the x. Let's determine the domain, range, and horizontal asymptote. Okay, so let's go ahead and graph it first. And the easiest way to graph a function is just to pick points. Let's make an XY chart and pick points. So here's x, and y equals 2 to the x. And I'm going to pick, let's get some numbers going. Let's go from -3 to 3. -3, -2, -1, 0, 1, 2, 3. Okay, I guess I should bring out my graphing utilities. Let's do it. Hey, look at that. Who's up already? There you go. So we're graphing 2 to the x. So I'll say 2 raised to the x power, enter, second table, and -3, -2, -1, 0, 1, 2, 3. Okay, look, and there's my values. So I get 0.125, I get 0.25, 0.5, 1, 2, 4, 8. Okay. So let's go ahead and plot those points and come back to the notes. Okay. So let me go ahead and spread my x values out. Why not? Here's 0, 1, 2, 3, -1, -2, -3. And the highest we go is 8, so I'll leave those y values alone. Okay. So there's 1, and then there's 8. All right, let's plot this function. So at -3, I just need that part. At -3, I'm at 0.125. So that's basically, let's see, going to be too big? Yeah. We'll say right there. At -2, we're at 1/4, not much higher. -1, we're at 1/2. 0, we're at 1, which is perfect. And then 1, we're at 2. 2, we are at 4. And 3, we are at 8. Okay, let's go ahead and connect our points. And if I do so, coming from -infinity, I'm going to get really, really close to the x-axis, but I'm never, ever going to touch the x-axis. We'll get more into that. And here's what our exponential function of 2 to the x looks like. Okay, so there's a reason why we never ever touch the x-axis, and that's just based on the properties of this exponential function 2 to the x. Honestly, it's the properties of every exponential function why you won't touch the x-axis. So let's explore that with the calculator. So looking at my values on the left, let's say I go more negative. Let's say I choose -4, -5, -6. Look at my numbers. 0.625, 0.3, 0.015. What if I chose -10? That number is basically 0.00098. So what you see is that no matter how far we go, we're going to get really, really, really close to 0, but we will never touch the x-axis, no matter how far you go. So another great representation is, let's use Desmos. Let's see. Yep. Let's check this out. And let's graph the function 2 raised to the x. Now look at that. There's the function we just graphed. And now look as x heads towards -infinity. It looks like we are touching the x-axis. But if I run my finger along this, of course it says y is going to be 0, because this means that the decimal value is probably 0.00000.1001, which means technically that's 0, but technically you are still not touching the x-axis. So if I happen to zoom in really, really close, look at this. Let's look at negative, whatever number it's going to give us. Look at that separation already. Oh my goodness, look. So how much I zoom in, this still means we have not touched the x-axis. Now I can run my finger along it and look at those decimal numbers, 0.00262. That's basically, we're saying 0. And if I keep going, keep going, keep going, look at this, keep scrolling, we see that now, look at this, 0.0091, 0.0098988. So what we're saying is that we get really, really close to 0, but we will never, ever touch, which means that there must exist a horizontal asymptote there. So this will never, ever touch 0. And then the right side, your y values just head off towards infinity. Okay. Back to the notes. Okay. So this means that determine the domain, range, and the horizontal asymptote. Well, from the graph to the right, the domain, this tail is headed towards negative infinity, and this tail is headed towards positive infinity as x gets closer and closer to infinity, right? As x gets larger and larger and larger towards infinity. So our domain is all real numbers. Our range, well, one thing's for sure, we will never ever touch 0. So guess where we start? We start at parentheses 0, and my tail heads up towards infinity. All right, and now since we know we'll never ever touch 0, well, there happens to be a horizontal asymptote of y equals 0. There you go. And that is the graph of an exponential function whose base is bigger than 1. Okay, so next page is some properties about the exponential function we just graphed. So properties of an exponential function whose base is bigger than 1. The domain is a set of all real numbers. Using interval notation, the range is the set of positive real numbers, 0 to infinity. That's exactly what we wrote up there. There are no x-intercepts, but you will always have a y-intercept at 1. Look at that. We've got a y-intercept at 1. The x-axis, or the line y equals 0, is a horizontal asymptote as x approaches negative infinity. So by some calculus notation, which is what you see right here, with the way you say this is you say the limit as x approaches negative infinity of the exponential function a to the x, or the limit as x approaches negative infinity of a to the x will equal 0. So we know the line will approach 0 but never touch. So that is the basic definition of a limit. Okay. F of x equals a to the x, where the base is bigger than 1. It is an increasing function and 1 to 1. Let's check this out. This is an all increasing function. When you read it from left to right, this graph is all increasing. And if you draw a horizontal line through it, you only intersect it once, meaning the exponential function is a 1-to-1 function. Okay. The graph of f contains the points 0, 1, 1a, and negative 1 and 1 over a. We can prove that by our chart. So it says you'll contain the points 0, 1, 1 in the base, and negative 1 and 1 over the base. So if you were to plug that in, 2 to the negative 1 is just 1 over 2, which is 0.5. So we contain all 3 points that those properties state. Okay. And the graph is smooth and continuous with no gaps, breaks, or holes in it. Okay. So this is what the basic graph of an exponential function whose base is bigger than 1 will look like, unless we applied some type of transformations, right? Like, let's just take a quick look. Let's say we applied well, that's 3 to the x minus 3. But let's say we had something similar. Let's say my transformation was 2 times 2 to the x minus 3. This means by transformations, first off, that would be a vertical stretch. So you would take all of these y values and multiply them by 2. And then next, this is a horizontal shift to the right by 3 units, which means you would take all of those x values and add 3 to them. And boom, your transformation would be done. So, like I said, transformations can be applied to anything. Okay. Now let's look at an exponential function whose base is between 0 and 1. So this base is 1/2, which means it's between 0 and 1. So let's go ahead and graph this function. Well, fair enough. Easiest way to graph a function is pick points. So I'll have x and y equals 1/2 to the x. And here's my xy chart. And we'll choose the same numbers as the last one. -3, -2, -1, 0, 1, 2, 3. Okay, calculator time. And we're going to type in 0.5, which is basically 1/2, raised to the x. Okay. And then second graph. Hey, look, the numbers are there ready from the last one. So -3 will give me 8, 4, 2, 1, 0.5, 0.25, 0.125. All right, excellent. Now, let's graph. I can spread my intervals out again just for the x values. 0, 1, 2, 3, -1, -2, -3. And let's plot again. -3, 8 is going to be here. -2, 4 there. -1, 2, 0, 1, 0.5, 0.25, 0.125. And now we're going to have the same situation as the last graph. So we notice that as x heads towards infinity, we see that my y values start to approach 0. But will they ever touch? And the answer is no, they will never touch. And this is the graph of 1/2 to the x. Okay. Where again, since we'll never, ever, ever touch the x-axis, we'll have another horizontal asymptote at y equals 0. Okay. And then from this graph, once again, the domain is all real numbers. The range is still the same, 0 to infinity. And your horizontal asymptote is y equals 0. There you go. Now, these are the properties of a function whose base is between 0 and 1. 1/2 is between 0 and 1. And now let's look at those properties, which are on the next page. If we have an exponential function whose base is between 0 and 1, like I've been saying, the domain is still all real numbers, and the range is still 0 to infinity. Once again, there are no x-intercepts, but there's a y-intercept at 1. Right there. The x-axis is a horizontal asymptote as x approaches infinity. So what we say now in our limit notation from calculus is that the limit as x approaches infinity of a to the x equals 0. So all that says is as x approaches infinity, so as x heads out this way, your y values get closer and closer to 0. We see that. They get closer and closer to 0. They'll never touch, but we assume that at some point in time, we can just round and assume it approaches 0. All right. And the way written below in that calculus limit notation is the limit as x approaches infinity of 1/2 to the x will equal 0. There you go. A little bit of calculus for you. Yeehaw. Okay. If the base is between 0 and 1, it's an all decreasing function and still 1 to 1. This function is all decreasing. And if you draw a line through it, you only intersect it once, which means we're 1 to 1. And then the next one says that you will contain the points 0, 1, 1 in the base, 1/2, and -1 and the reciprocal of the base, which is 2. It all checks out. And then the next part says this graph is smooth and continuous and contains no breaks, holes, or gaps in it. Okay, marvelous. All right. Oh yeah, before moving on, if you think about transformations and exponential properties, actually, if you think about exponential properties and then transformations, there could be another way to graph this. So you could rewrite this function. 1/2 is basically 2 to the -1 by the negative exponent property. And now you have 2 to the -1 raised to the x, which means this would give you 2 to the -x. And if you think about transformations now, the negative in front is a reflection. So the negative in front of the x is a reflection across the y-axis. Which means that all we had to do was take the original 2 to the x and just flip it over the y-axis, and we would have had our graph here. So, something to think about. All right, now on to the number e. All right. Yes, it's not a letter anymore, guys. It's a number. And this number e occurs in business modules, exponential modules. The best example, well, it also occurs in growth and decay models. But all of those can be combined for the most important part for number e is about money, right? The number e is used in something called continuous compound interest. let's say you put in a certain amount of money for a certain number of years. Well, when you plug it into this formula, what the continuous compound interest formula does, it says, hey, this amount of money, let's say you put in $1,000. Your $1,000 is making money every second, every minute, every hour, every day, every week at a certain interest rate. It is continuously compounding. Now that is actually awesome if you're investing. If it's a student loan, that's the same thing that's going on too, which is the one we don't want. So the number E is really awesome. It's used in a lot of applications. All right. But I think the most important one is the money one, right? Okay. So I guess it depends on your profession. All right. So where the number E comes from is this lovely expression. The number E is defined as the number that the expression 1 plus 1 over n to the nth power approaches as n approaches infinity. In calculus, this is expressed using limit notation, such as the limit as n approaches infinity of 1 plus 1 over n to the n will equal E. So let's find out what that number E is. Let's play around with the graphing calculator. Let's put this expression in, right? Maybe I'll make a little XY chart over here. Just for the number, just for E, right? So I'm going to type this expression into my calculator first. Somehow, let's see, 1 plus 1 over x raised to the x power. And then second graph, let me delete everything that's here. Okay, so I'll just make a small XY chart. Let's have fun, right? So for x, so we have to get infinitely large, right? So if I start with 1, I get 2. Now when I say infinitely large, think big. Let's go from 1 to 100, and I get 2.7048. Let's up it up another notch. Let's go to 1,000. I get 2.7169. And then let's keep adding on zeros. 10,000. 2.7181. Let's add on another 0. 100,000. 2.7183. And let's just add on one more 0. Let's make it 1,000,000. And then if we kept going, I'm not going to write it on paper, but I'll put it on the calculator. No matter how much larger x gets, we see that we come out with this decimal number, 2.7183. Or 2.7, well, that's rounded, right? 2.7182, run on, run on, run on, run on. This is the actual number for E. So we can say that E is approximately 2.7183, which is an irrational number just like pi. That decimal number will run on and run on and run on and run on forever, just like pi. So our big takeaway is that this is called Euler's number or Euler's number. It is the number E. It is used in a bunch of applications. Just know that its approximation is 2.7183, and it comes from this expression. All right. So pretty crazy, huh? All right. Now let's actually graph the exponential function e to the x. So we take this number e and we raise it to the x power. So let's see what that looks like. So we'll have our XY chart. And I definitely recommend you researching more about E. See where it comes from, see who found it, everything about it. It's really cool. Okay, like how did you find this number? It is the natural occurring number in nature. It helps you find the decay of a population, the growth of a population. It's insane. It's cool. Okay, so back to this. We're graphing. So how do you graph e to the x? You use the same method that we used above in the last two problems. Let's go ahead and pick the most popular numbers. -3 to 3. And go back to my y equals, clear that out. I'm going to say second natural log e to the x. There it is, e to the x. All right, and then second graph, delete whatever's here, and type in -3, -2, -1, 0, 1, 2, 3. All right, and 0.0498, 0.1353, 0.3679, 1, 2.7183. Hey, that number looks familiar because that's e to the first power, which is just e, which is just itself. 2.718, yada, 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 right? And then 2, 7.3891. And then 20.086. Okay, perfect. Now let's graph. Just need that part. Okay. Once again, I'll space out my x-axis. 0, -1, -2, -3, 1, 2, 3. And then my y values shoot up to 20. Let me start at 1. We'll just leave it alone. We'll leave it as is. We don't have to graph to 20. Okay. So start off at -3. -3, you're at 0.0498, which is 0.05, which is barely above the x-axis. And then -2, you're at 0.13 or 0.14, not much higher. And then -1, you're at 0.36, 0.37, still not much higher. And then 0, you're at 1. And then 1, you're at 2.78, the value of e. So 1, 2. I'll just put that right below 3. If I can get it right on the money. There we go, somewhere around there. And then 2, you're at 7.3891. 3, 4, 5, 7. There. And now let's just connect. And that is the graph of e to the x, which looks just like the graph we did in the beginning, 2 to the x. Shares the exact same properties because e is a base bigger than 1. Remember that e's base is basically 2.7183. Right? So it's a base bigger than 1. So it's going to represent an increasing exponential function. Okay, and once again, looking at the graph, your domain for e to the x is still all real numbers. Your range is still 0 to infinity. We'll never ever touch 0. And once again, since we never ever touch 0, you'll get a horizontal asymptote at y equals 0. All right, not bad. That is e to the x and all its mysteries and possibilities. Definitely look more into it. It's very interesting. Okay. So there's that, and then what's next? We're done with graphing. We can move on to exponential equations. Let's see and make sure I'm not missing anything. When you get, because you guys will be graphing, you will be graphing e to the x and any type of transformation to e to the x. So just remember how to work transformations. Let's say we were given a function y equals -5 times e to the, let's say, x plus 1. Oh, minus 2. Look at all those transformations, right? So first thing we would say is that -5 is a vertical stretch. Also, the other first thing we would say is that negative reflects over the x-axis. And then that +1 would be a horizontal shift left. And then this -2 would be a vertical shift down. So nothing has changed from that section we did transformations in. So the negative would take all of your y values and make them negative. And then, while you're making them negative, this 5 would then multiply all of those by 5. And after you multiplied all of those by 5, you would then subtract 2 and shift them all down. So the transformation would be flip it, stretch it, shift it down, and then the very last transformation you would do is the x plus 1, which means you would take the x values and shift them to the left. So it'd be a reflection, a stretch, a shift down, and a shift over to the left. Everything we know about transformations. Nothing new. The only thing new here is now we're dealing with a different type of function. But all the transformations would remain the same. So if you were, what would that look like? First you would reflect it, and then you would stretch it, which means that it would probably look like this stretched. And then you would shift it down, which means it would probably go there. And then you would shift it to the left by 1 unit, which means you'd probably have, well, curvier, of course, but you'd probably have something that looks like that. And there you go. Yeehaw. Okay, that is graphing exponential functions. How do you graph something? Easiest method, pick points. You don't have to pick from -3 to 3. You can pick from -2 to 2. Just get as many points as possible so you have enough information to graph it. Okay, now the fun parts. Solving exponential equations. All right. So equations that involve terms of the form a to the x, the exponential function, where the base is greater than 0 and not equal to 1, are referred to as exponential equations. Some equations can be solved by applying the laws of exponents and a property such as, so here's a new exponential property. If a to the u equals a to the v, if you have the same base on both sides of the equation, then you can set the exponents u equal to exponent v and solve for x. That's it. So remember your exponential properties when solving these. Okay. So number 1, 3 to the x plus 1 equals 81. Well, we want to use this property. But in order to use this property, we need to have the same base on both sides. Well, here's where we think to ourselves. Can you write 81 as a base of 3? And that answer is yes. You can write 81 as 3 to the 4th power. That's it. So 81 becomes 3 to the 4th, because 3 squared is 9, 3 cubed is 27, 3 to the 4th is 81. If you don't know your squares, cubes, fourths, fifths, sixths charts, definitely look it up. It's worth the research. Okay. And now we can use that property from above. We have a base of 3 here and a base of 3 there. And according to this property, if we have the same base, then you can go ahead and set the exponents equal to each other. Which means you'll get x plus 1 equal to 4, and x just equals 3. Not bad, right? Now that's fun. That's some algebra for you. All right. 2, 4 to the 2x minus 1, and 8 to the x plus 3. Once again, we need to have the same base in order to use that property above. So we know that 4 and 8, so you can't write 8 as a base of 4, and you can't write 4 as a base of 8. But we know that 4 and 8 share a common base of 2, which means 4 can become 2 to the 2nd. So 4 is 2 squared. And now what we do is we take this 2 and multiply it to whatever exponent was there already. So you get 2 times 2x minus 1. And then 8 can be written as a base of 2. 8 can be written as 2 to the 3rd. And once again, this 3 will multiply whatever exponent is there already. Okay. And now, do we have the same base on both sides? Yes, we do. So this means you can set the exponents equal to each other. And solve for x. Yeah. Put a little arrow there showing what we did. Because every now and then somebody asks, where did these 2 go? And the 2's went away because we're using that new exponent equality property on the top of the page. So 4x minus 2, 3x plus 9. Move the x over, get x, move that, you get x equals 11. Okay. Now for some good stuff. Okay. e to the negative x squared equals e to the x raised to the second times 1 over e cubed. Okay, so we want to use that equality property again on this, but remember, in order to use the equality property, there has to be a single base on both sides. There can't be another base here if we use it. So we have to figure out, how do we get this to one single base? Which means we have to rewrite the right side of this equation. The left side, perfectly fine. So this will stay e to the negative x squared. And now we must simplify the right side using exponential properties. So first up is e to the x squared. You have power to a power, which you would put together by multiplication. So that would become e to the 2x times. And now we need to figure a way how to write 1 over e cubed. What is another way to rewrite this? And another way to rewrite this, we'll use the negative exponent property and rewrite this as e to the negative 3. So this uses this property. We have taken 1 over x to the n, or 1 over e to the third, and rewritten it as e to the negative 3. That's it. That uses the negative exponent property. Okay. And then, same base on both sides, we have another exponential property. If you have the same base, you add the exponents together. So you'll get e to the 2x plus negative 3, or we had just leave it as e to the 2x minus 3. This used x to the m times x to the n gives me x to the m plus n. All right. And I guess I could show this one, right? This one used x to the m raised to the n gives me x to the m n. There you go. Look at all these exponential properties that you remember, right? Okay. And now we get to use that equality property. Same base on both sides. We've narrowed it down to a single base on both sides. Set the exponents equal to each other. Oops. And solve for x. There you go. That's all we did there. And now we have a lovely quadratic equation, which means I'm just going to add that x squared to the right side. 0 equals x squared plus 2x minus 3. Factor it, x plus 3, x minus 1, x squared negative x, 3x, 2x. And we get x equals negative 3, x equals 1. Look at that. That's a good time right there. Okay. Solving these by using nothing but exponential properties. That's how you solve these exponential equations. Okay. Let's do it again. Last one, I think. Good. 4 to the x times 2 to the x squared equals 16 squared. All right, so we want to use that equality property, which means we need to get a single base on both sides. Well, lucky for us, 4, 2, and 16 all share a base of 2. So 4 to the 4x becomes 2 squared x. So we can rewrite 4 to the x as 2 to the 2x. And then 2x squared is perfect as it is. So we'll leave that as 2 to the x squared. Equal to, now 16, you need to rewrite as a base of 2. So 16 becomes 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16. So you get 2 to the 4th times 2. Here, I'm going to put a parentheses there just to show we have to multiply that. Okay. So let's clean this up a bit. 2 to the 2x times 2 to the x squared equals 2 to the 8th. And now, by our exponential properties, same base, add your exponents. So this will give us 2 to the 2x plus x squared equals 2 to the 8th. And now you have the same base. So we can use that equality property from above. So here I'll write it in these terms. 2 to the a equals 2 to the b means a equals b. Which means now you'll get 2x plus x squared equal to 8. And then move the 8 over. We have a quadratic equation. Rearrange it with highest power first. X squared plus 2x minus 8 equal to 0. Factor it. X plus 4, x minus 2 equal to 0. X squared, negative 2, 2, and x equals negative 4, and x equals 2. And there you go. That's how we solve these exponential equations. Feel free to check your answers as well by plugging them in. If I plugged in negative 4, I'd get 4 to the negative 4, and then times 2 to the 16th, and then 4 to the negative 4. Maybe negative 4 doesn't work. Let me see. 4 to the negative 4 times 2 to the negative 4 squared equals 16 squared. I'll make this 2 to the 2 times negative 4 times 2 to the 16 equals 16 squared. So give me 2 to the negative 8 times 2 to the 16th, which gives me 16 squared. Add those together, you'd get 2 to the 8th. And 16 squared from earlier was 2 to the 8th. Hey, so it does check out. So always good to check your work as well. Okay. Let me rewrite this one. Let's say, since we're doing same bases, let me see. There we go. Okay. Those are exponential functions. That's how you graph them. That's how you solve them. Bring out those exponential properties that you've been hiding since 0320 and have fun. Okay. That is it. See you at the next one.